Let me just start my recording as well. Um, okay, so for the next talk, we have Elijah Sheridan from Cornell University, who's going to tell us about cohomology formulae and holes in effective cones for D-brane physics. Go ahead.
Perfect. Thank you so much. Sorry, I'm just trying to get my Zoom figured out here. This should be good. Okay. Um, Great. Thanks so much, the organizers, for giving me an opportunity to talk in the virtual seminar series here. My name is Elijah. Today I'm going to talk a little bit about formulas for cohomology and holes in effective cones for deep brain physics. This is based on a paper that came out a few months ago with Naomi Gendler, Mike Stillman, and David Wu, holes in effective cones, as well as an upcoming work with Andre Constantine and Andre Lucas. Um, to give a kind of bird's eye view of what I'm going to be talking about today, I'll recall that to achieve one of our goals in string phenomenology, namely constructing UV models of physics and then studying the low energy infrared consequences at scale and doing this efficiently and doing this for diverse models, we often have to solve kind of intricate mathematical problems in order to actually translate the UV data that we start with into low energy predictions. And so with this in mind, today we're going to study one of these mathematical problems. In particular, we're going to study the structure of line bundle cohomology and some kind of recent progress that I've been thinking about in this area. So that being said, let me give an overview for the talk. I'll begin by giving a little bit of motivation why you should care about the kind of low energy data that you can derive by performing line bundle cohomology calculations, in particular, the way that this is important for D-brane physics. Then I'll talk about the primary strategy that we employed for actually making progress in understanding the structure of this cohomology, namely by employing birational geometry, which I'll say a little bit more about momentarily. And I'll talk about some results that we found, namely a phenomenon we refer to as holes in effective cones, as well as I'll make some comments about ways of achieving closed form formulas for cohomology. Great. So let me start by giving a little bit of motivation using D-brane physics. First, I want to think about D7 branes and compactifications of type 2B string theory on Calabi threefolds. And the question that I want to ask and think about briefly is what are the low energy degrees of freedom that live on D-branes? If I imagine wrapping a D-brane, a D7 brane on the Minkowski four dimensions and four compact dimensions, some compact four cycle. Um, Kind of core fact about D7 branes is that they host gauge theories on their world volumes. And there are fields in the low energy spectrum that are charged in these gauge theories arising from open strings ending on these D-branes. Um, the particular details here aren't especially important. For example, you have adjoint valued scalars as well as bifundamentals charged under multiple gauge groups arising at intersections of these D-branes. The point that I really want to stress is that you have some charged degrees of freedom in the infrared, and they're counted by line bundle cohomology, either zeroth line bundle cohomology or higher line bundle cohomology on these intersection curves where F here denotes a world volume flux that you've chosen for these D7 branes. But the point here is really this isn't going to be a talk in gory detail about D-branes. The point is that these things that you care about are counted by line bundle cohomology. Why should you care about these degrees of freedom? Well, one reason is that intersecting D7 brane models are among the more kind of promising and interesting ways of getting realistic visible sectors in type 2B. So there's a kind of illustrious tradition of this. And in particular, there's an ongoing project that I'm thinking about where we're trying to construct realistic visible sectors at scale in the Kreisler-Skarke database. And so this has been on my mind. This is something that's very important. An additional important D-brane contribution to the low energy theory is from Euclidean D3 branes. And so the question I want to ask here is, when do these Euclidean D3 branes wrapped on compact cycles contribute to the four-dimensional superpotential? This really is, again, a question about counting degrees of freedom, but I'm going to phrase it in this way. So, as solutions to the Euclidean equations of motion, we're accustomed to objects like this contributing to semi-classical expansions of the path integral, and giving us 10D solitons, or in 4D, where they're point-like in Minkowski space, they act as instantons. But the holomorphy of the superpotential strongly constrains which Euclidean D3 branes wrapped on which cycles can actually contribute to the superpotential. And people have understood certain sufficient conditions, topological conditions for these cycles, namely they need to be effective and rigid. Again, the details here aren't incredibly important. The point is that there's certain again, line bundle cohomology calculations that you have to do in order to determine which force cycles actually yield contributions to the superpotential. You need these criteria to be satisfied. Again, maybe so what? But ED3s kind of crucially provide several important contributions to the low energy effective field theory in type 2b. For example, it's crucial. It often provides the leading order potential for the Kähler moduli, providing Kähler moduli stabilizations, such as in the KQLT scenario. And this also provides the kind of dominant potential for C4 axions. So studying the string axiverse in type 2b, as has been done extensively, and this is very near and dear to my own heart, this requires an understanding of the superpotential and ED3 contributions to the superpotential. So hopefully you maybe at least partially believe by this point that computing line bundle cohomology is important for understanding IR information arising from string compactifications. I also have just talked about 2b. This is also incredibly important in the heterotic string, for example. So what's the state of the art? We can compute line bundle cohomology for simple examples with sufficiently few moduli, but it's an expensive computation. And it's also a little bit of a black box. We have codes that can perform these computations, but we don't really have a great understanding of the structure, such that basically every time we want to do a new computation, we have to plug in into something and start over from scratch. So I want to focus on two kind of specific questions today that hone in on particular aspects of this question of line bundle cohomology. First of all, I want to ask, can we understand the number of global sections that divisors have or line bundles have on Calabi threefolds? Can we compute this number? Can we understand its structure? And this is the subject of the ongoing work with Andre and Andre. And then an even more basic question, which might seem almost too trivial, but turns out to have actually rather interesting structure, is kind of setting aside what the number of these global sections is, can we determine whether it's zero or not? And this was the subject of the paper that came out a few months ago. Okay, so I've given a little bit of background. So now I want to talk a little bit about the strategy. And I'll begin by setting a little bit of notation. I'll do this relatively quickly. By divisor, I roughly mean in this talk a linear combination of complex codimension 1 submanifolds that in particular are algebraic, are kind of defined by polynomial equations. And as is familiar from, de Rham cohomology or singular homology, I'm going to let the term divisor class denote a homology class of divisors. I've already alluded to this fact that you should maybe be thinking about divisor classes and line bundles as roughly being in correspondence. As a quick review of this, the kind of local equations that define divisors turn out to be exactly the right data to define the transition functions of a line bundle. And conversely, the first Chern class is a map from line bundles to homology classes. And so this is why I can kind of freely interpolate between these two pieces of data, and I'll kind of do so throughout this talk. Finally, I'll recall that a divisor class is effective if the associated line bundle has global sections. And the associated group of global sections is non-trivial. Intuitively, this means that there actually exists some algebraic submanifold that represents this divisor class. There actually is some submanifold in this class. And note that this is basically the same condition that I posed for question number 2 on the previous slide. When do we have a non-zero number of global sections? So this is equivalently, when is a given divisor class effective? This might sound like almost too easy of a question because as soon as you make the observation that sums of effective divisor classes are also effective, which just follows because if I have two effective line bundles, D1 and D2, and I pick sections of them, and I take their product, that's a global section of their sum. And so it seems like I should really just take the cone generated by all effective line bundles, all effective divisors, intersect this with the lattice, H sub 4, and this should give me all of the effective divisors for whatever variety I'm considering. So I've given a little schematic here. The hollow circles are non-effective divisors. The filled in circles are effective divisors. You imagine that there's just some cone that they generate shaded in red. And every lattice point that's in that cone is some effective divisor. Unfortunately, this picture is just a little bit too simple. And this was the motivation for this paper that came out a few months ago. It turns out that there are kind of non-trivial lattice effects. In particular, the divisor classes that are effective actually form some kind of, in general, non-trivial semigroup contained in these lattice points in the effective cone. So a kind of more accurate schematic would be where, in addition to having all of these non-effective classes outside of the effective cone, you also have some inside of the effective cone. And these are highlighted in blue here. And so in this paper, we referred to all of these lattice sites in the effective cone that are not themselves effective, but merely in the cone generated by effective things. We refer to these as holes. So this is what I'll call these for the rest of the talk, holes in effective cones. So I posed some questions that I'm going to try and answer today, and I'm about to go into some technical details. So just to give you all a sense of kind of where we're ultimately headed, to kind of give you something to hold on to and something to anticipate, something to look for, I'm going to give you the answers, some of the primary answers to these questions up front. So first we asked, what is the number of global sections in general of effective divisors? And it turns out that on the interior of the effective cone, this number of global sections is given by a piecewise closed form formula. There's a formula that you can write down that captures these numbers of global sections, where the input data that's needed to determine this formula comes from birational geometry calculation and features the intersection numbers of the geometry of interest. So these are things, the point is that these are things that are totally computable, as I'll elaborate on momentarily. And then for our second question, when do we have a non-zero number of global sections? When do we have an effective divisor class? In particular, now we kind of see that the non-trivial part of this question is, when do we have holes? When do holes arise in the effective cone? Um, the answer that I'll converge on is that holes do exist. And in particular, they seem to come in families. They aren't isolated. They kind of come in countable collections of holes. So these are the things that we're going to try and converge toward. Okay. So let me try and present some of the more technical aspects of the way in which we went about understanding the structure by talking about the kind of dictionary or relationship between cohomology and birational geometry. The kind of key cornerstone idea is that any divisor D defines a rational map or a map that isn't defined everywhere. It can have poles in places, but a map defined on a dense open subset of the variety, which is given by taking any point in the variety and mapping it to a linearly independent basis of global sections at that point. And letting these define homogeneous coordinates in an image projective space. Because these are sections and not actual functions, these are only defined up to an overall rescaling, but this is fine. This is exactly how homogeneous coordinates on projective space work. They're well defined up to scaling, so this is fine. So we define some rational map into projective space with any effective divisor that we have. What this means is that the structure of global sections of a divisor is kind of intimately linked to the birational geometry of whatever Calabi threefold you're studying. If this is a new term, this is a little bit of a technical math term, but what birational geometry just means is birational maps are isomorphisms between varieties that hold on dense open subsets. So they're isomorphisms kind of up to measure zero subloci. And kind of more practically, some words you might be more familiar with are operations that you can apply to Calabi threefolds, like flops or conifold transitions or blowups and blowdowns of divisors. These are all examples of birational maps, roughly. And so when I talk about the birational geometry of a Calabi threefold, I mean that all of the varieties you can kind of produce by performing these little surgeries. And in particular, these maps F sub D are going to give rational maps to these different birational transformations of the Calabi threefold that you start with. But let me provide some explicit examples, or rather some kind of case studies. First, I want to consider the case that I have some divisor who has a divisor class that has a fixed component, by which I mean there is some other effective divisor E, which belongs to the zero locus of all global sections associated to this divisor. So what does this mean with respect to this map F sub D that I defined? What it means is that at every single point on this divisor E, the map F sub D maps this to the homogeneous coordinates where every single coordinate is zero, which you might recall is forbidden for a projective space. You actually excise the point of all zeros. And so the interpretation is that F sub D actually just removes or contracts or shrinks this divisor E. It is totally blind to it. E is an exceptional divisor of this map. Um, from a cohomological standpoint, if this E belongs to the zero locus of every single global section, then this means that all global sections factorize and have an overall prefactor of a section S sub E of the line bundle associated to E, uh, such that you get this reducible structure. Um, and the reason that this will be important to us is because there's this overall factor of S sub E in all of these sections, dividing by S sub E, or equivalently subtracting the class E from D, uh, will result in no loss of sections. So I've said a lot of words here. Let me draw some pictures really quick to kind of illustrate this. So what I'm imagining here is taking some generic section of a line bundle, and if it has a fixed component, then it has this factorization structure, which means that you have some piece that in the zero locus that corresponds to this overall factor vanishing, and some piece that corresponds to the remaining part vanishing. And as I vary the section in the line bundle associated to D, maybe I slightly change what this factorization looks like, what the second factor looks like. So I'm kind of slowly moving and warping this additional piece associated to the different F sub i's. But I always have this S sub E prefactor, which means that I always have what I've modeled here as this circle. I always have this circle present. This is contained in every single divisor in this divisor class. To elaborate slightly on exactly what I mean by nothing is lost, by subtracting E or dividing by S sub E to write a kind of mathematical explanation of this, if all of my sections are of this factorized form, then I'm free to take the part that is not S sub E, which must belong kind of by the rule I talked a little bit on the previous slide about effective cones. It must belong to the line bundle D minus E. And I haven't given you a proof of this, but it turns out that one can show that this means that removing this fixed component from the class does not change the total number of global sections. People that think about F theory might kind of recognize this. This is the phenomenon that E is this non-Higgsable cluster associated to D. If I imagine D as being some D-brane or some kind of lift of a D7 brane to F theory. So if you want to do some kind of word association, then that's exactly what I'm talking about here. Okay. Let me talk about a different example. Positive divisors. So what do I mean by a positive divisor? Now I want to consider some divisor such that it, or maybe one of its multiples, has no fixed components at all. There is kind of no submanifold that is stuck in this divisor class. And I also want to assume that I additionally don't have any higher codimension kind of fixed components. There is no point in my variety where all of my global sections simultaneously vanish, no base points. What this means now is that if it's some multiple that has this property, then the associated rational map is actually well-defined everywhere. There isn't any point that it maps to homogeneous coordinates of all zero, which means that it actually defines an isomorphism. It defines an embedding of the variety you started with into projective space. And I'm going to roughly refer to this as positivity. The reason that I'm not using a more kind of specific adjective is because kind of depending on the theorem you want to apply, or depending on what you're trying to do, depending on how you're trying to use positivity, there are a set of closely related but distinct notions of positivity that are relevant. You may have heard of the ample condition, the very ample condition, the Neff condition, being big, being movable. I don't really want to get bogged down in these kind of technical details. I'm happy to answer questions about it. But I'm going to kind of just generally refer to divisors as being positive when I mean it has some kind of quality like this. Why do we care about this from a cohomological standpoint? That's because it turns out that the global sections of positive divisors is actually straightforward to compute using intersection theory by chaining a set of results from algebraic geometry. So let me kind of break this down piece by piece. First, for positive divisors, vanishing theorems, such as the Kawamata-Vieweg vanishing theorem, informs you that higher line bundle cohomology vanishes, which means that the zeroth line bundle cohomology coincides with the alternating sum over all line bundle cohomologies, because you only get a contribution from the first term. But this quantity is the holomorphic Euler characteristic of the associated line bundle, this chi, just by definition. And there are powerful theorems such as Hützelberg, Riemann, Roch that relate this Euler characteristic to a characteristic class computation, which all you need to store away about this is that it's something that's very computationally feasible. You can do it with intersection theory, which you should store in your head as just a straightforward computation. This is something that's actually practical and something that you can do. So these positive divisors, their global sections can be straightforwardly computed.
Elijah, just to
Okay,
let you know, you have 5 minutes left.
thank you so much. Um, so uh, to talk about the strategy for how we're going to employ this, what we've learned is that we can freely remove fixed components or overall factors in global sections while preserving the number of global sections. This is something we can do freely. And also, if we can reduce to positive divisors, it suffices to compute the number of global sections using intersection theory. So if we have some scheme where we can always remove fixed components until we're left with a positive divisor in the end, we win and we get some formula by kind of composing subtraction with evaluating the holomorphic Euler characteristic. This might sound great, but it actually is not quite so much of a free lunch because in order to kind of figure out what the fixed components even are and when divisors are positive, it kind of seems like we needed to know the global sections to begin with. After all, this has to do with how all of the global sections factor and such. The real insight is that birational geometry is related to this fixed component structure, this positivity structure. Birational geometry tells us that the fixed components are these divisors that are contracted or shrunk by birational maps. Um, and moreover, that the regions in the effective cone where you have particular fixed components or you have particular positivity form cones, like the Kähler cone. And all of these cones, as well as these fixed components, are computable things. In particular, the great paper moduli space reconstruction explaining how to construct Kähler cones and the extended Kähler cones. The point is that these things are computable, and we can put this to work to try and understand cohomology. So I'm running out of time, but let me try and sketch a little bit about how this goes in practice by giving you a picture. So here's a picture where I've chosen some geometry that has H11 equals 2 linearly independent divisors, and the effective cone is the positive quadrant. I've illustrated the Kähler cone here, which is the cone of positive divisors in this case, where cohomology calculations, line-bundle cohomology calculations are straightforward. And then these other two green chambers where you have fixed components. In particular, it turns out that the particular exceptional divisors that give these kind of overall factors that can be freely subtracted are generators of these green cones. They'll always be extremal rays. And so the prescription is for each of these green cones, you take divisors in them and you systematically subtract off these particular generators of the cone until you end up in the red region, this preserved global sections, and you can safely evaluate with an Euler characteristic at the end. Um, I'm running out of time, so I will probably just put this on the screen. I wanted to present an example with actual holes. And we can see why the holes must come in families now, because if they arise kind of outside of this positive region, this region with fixed components, then we know that anything that subtracts to one of our holes by subtracting off these fixed components must also be a hole. And so these don't come alone. They come in families. They come in countable families. Um, so maybe in my closing couple of minutes, I'll just put this on the screen. The kind of primary results that we had from the first paper, this paper on holes, was we characterized where in the effective cone that holes can actually arise. We talked about how holes kind of seem to always come in families. And we also connected holes to this interesting phenomenon of kind of detecting when blowdowns of the original Calabi you were studying were not simply connected. We also showed some specific results that were specific to toric hypersurface Calabi threefolds and a kind of particular class of canonical holes that arise in that case. Also, in this upcoming work, we found that one can indeed systematize this process of subtraction and evaluation of the Euler characteristic with what you get out, and you get a piecewise formula where the domains of the piecewise function are the different cones in the decomposition of the effective cone. And the only place that seems to be kind of hard to evaluate in some cases are particular boundaries of the effective cone. But some boundaries can be evaluated and the interior can be evaluated and prescribed with a formula. Um, so to conclude, I'll recall that to understand various aspects of traversing from UV data to IR predictions, um, in particular the way in which D-branes impact this traversal, this motivates us to understand the structure of line bundle cohomology. Um, and by connecting it to birational geometry, we gain new insights into the structure of this cohomology. We found that holes exist in the effective cone, and we gained some understanding of their structure, such that they seem to come in these families. And we also were able to come up with methods for constructing closed form expressions for global sections just using computable birational data. And the more we understand the structure, the better that we can do computations at scale, string pheno at scale, and also do targeted searches for particular phenomenology that we're interested in. Um, Thank you so much.
Thanks a lot, Elijah. Do we have questions for Elijah? I'm not seeing any hands yet. Maybe I can ask you something in the meantime. Can you give me the, this is a bit abstract for the kind of thing I'm used to. So could you
Yeah,
give
yeah.
like a concrete, like a very simple example? For example, in when you were talking about using this to study D-brane models that could approximate a standard model, realize a standard model or something close like a toy model. Is there a simple way of seeing how this extra information that you're getting with your methods, what it tells you about this kind of models, about these D-brane models?
Yeah. Great question. So a one kind of I see. Okay, so for intersecting these separate brain models in particular.
Exactly. Yeah. Yeah. Sorry.
Yeah. Yeah. Good question. So um, for example, if you're interested in D7 moduli stabilization, for example, you want to know the kind of naively the number of kind of massless deformations that D7 branes have that you want to stabilize in order to achieve some kind of gauge group that you're interested in. And so you need to know the number of kind of linearly independent deformations that these D-branes have, and this is counted by line bundle cohomology. So if you have some geometry that you're interested in building a intersecting D7 brane model on, once you've picked the cycles that you want to host D-branes on, you would be able to use this technology to kind of quickly figure out how many moduli do I have to stabilize and what are they? And such you can kind of then start inspecting exactly what kinds of effects could stabilize them, for example.
I see. I see. Okay. Yeah. Yeah. Does it also tell you directly uh, properties of the world volume theory, or do you need extra like extra structure on this on top of this?
Yeah, so I mean, if you mean things like couplings and things like this, kind of more like continuous data, it's not going to immediately give you that. But if you're, for example, interested in explicitly building standard models, then you need to ensure that you have the correct number of, chiral generations, for example, and the number of generations of a number of standard model generations is also counted by a line bundle cohomology calculation. I hesitated to name that immediately because um, uh, that particular computation is slightly more complicated because it's happening on a subvariety of the Calabi and also involves higher line bundle cohomology. So the methods here aren't like necessarily directly applicable, but we're kind of building in the direction of that. Yeah.
I see. I see. Perfect. Thank you. Are there any other questions for Elijah? Okay, I don't see more questions. So let me thank you and Shu Ying again for today's talks. And we'll be back in 2 weeks for the final session of this semester. So we'll see you there.
Thanks so much.